We can occasionally use series to answer some problems that are hard to solve using a function representation. So this function, the integral of e to the negative x squared dx, would be, well, we couldn't do it using any of the techniques that we know, but if we know that e to the negative x squared can be written as a series, then we could write, okay, this is equal to the sum of, now instead of e to the x, we have e to the negative x squared, so we're going to replace our x with a negative x squared. So that was x to the n over n factorial. That was our first example that we did. And this, we've got alternating signs here, and we're doubling those powers of x's, if you look at that. So our first term is going to be a 1, and then a negative x squared divided by a 1 factorial, and then a positive x to the 4 over 2 factorial, and then a negative x to the 6 over 3 factorial, and so on. So we didn't prove that e to the x is equal to this sum. This sum is this representation, the series representation of e to the negative x squared. And we kind of skipped the proof that the proof part, and we're not going to do the proof part. So if we knew that this equals that, we could then replace this in for our e to the negative x squared, and then integrate term by term, which would give us x is the integral of 1 minus x cubed divided by 3 times 1 factorial plus x to the 5th divided by 5 times 2 factorial minus x to the 7 divided by 7 times 3 factorial. And you can see a pattern here, and the pattern is negative 1 to the n, x to the 2n plus 1 over 2n plus 1 times n factorial. So that would be our nth term of the sequence. Then that would be the integral. That would be, this is integral here. And if we wanted to evaluate the integral, now that's something we could do using fundamental theorem, using some kind of estimating, because at some point you're going to have to drop some terms. But the point is, series can be used to solve some harder problems. Here's another example of using series to solve a problem. If we have this limit, and we want to evaluate this, probably what you're thinking is, this kind of looks like L'Hopital's rule. We could just do 2 rounds of L'Hopital's rule and get the answer, and you would be correct. But we could also use the Parry series for our e to the x and use its expansion at 0, so that would be a Maclaurin series. So our e to the x is 1 plus x over 1 factorial plus x squared over 2 factorial plus dot 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 minus 1 minus x all over x squared. Now what you notice here is we've got 1 minus 1, x minus x, and then everything in here has an x squared term in it. So what we can do is factor that x squared term out. And what do we have? We have 1 over 2 factorial plus, you'd have an x over 3 factorial, and so on. And then we have x squared in the denominator. Simplify the numerator with the denominator. Now we can evaluate our limit because we took care of the 0 over 0 problem, and we're left with all of these terms is just 0 over a number. So all that's left is 1 over 2 factorial. 1 over 2 factorial is just 2. So there you have it. We could also make easy L'Hopital's rule problems look more complicated using series. Last thing that we can do is we can multiply series together. So if we had e to the x times sine of x, we can do the two series representations for e and for sine, and then FOIL it all out. Well, we'll pretend to FOIL it all out. You can't actually FOIL it all out since there's an infinite number of terms, but let's pretend like we were going to do it. From the table in the book, this is on page 768, we've got our e to the x there, and there's our sine x that we did previously. So what we have is 1 plus x over 1 factorial plus x squared over 2 factorial. We just did that one. And then times, so this is alternating, but it tells us x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on there. So the way to do this would be just to FOIL this out and keep things lined up. So if I were doing this there times there, that's the firsts, that would give me x's. And then next we would have the next one when we distribute. So that would be a minus. So I'm going to put a little bit of space here for my x squared terms, and then I have minus x cubed over 3, and then I would have leave a space for my x to the fourths, x to the 5 over 5 factorial, don't forget the factorials, plus and so on. Move this down a little bit. Then when I go into my next term, I have it's going to give me x times an x will give me an x squared over 1 factorial. The next one will give me an x to the fourth over 1 factorial times 3 factorial. And then the next would give me an x to the sixth over 1 factorial times 5 factorial, and so on. The next one we would have to line up with my cubes, and so that would go here. And the next would be to the, wait, did I get that wrong? Yeah, cubes, and then fifths, and then sevenths. Now, the original question says, find the first three non-zero terms. So the first three non-zero terms would be the x to the first, x to the second, x to the third terms. So I would need this, and I wouldn't really care about all of that stuff. So this would be the first three non-zero. I guess I should fill in this blank here. My last one needs to be, that would be an x cubed over 2 factorial. So whatever this is, is my answer. Let me move this down one more time. So what do we have? We have x plus x squared. Now, 2 factorial is just 2. 3 factorial is 6. So minus x cubes over 6 plus x cubes over 2. So you get your common denominator there. And I guess that'd be sixths. And let's see if I can do fractions in my head. I need 3 of those. 3 of them minus 1 of them is 2 of them. 2 sixths is a third. So my final answer is x plus x squared plus 1/3 x cubed. So that is the first 3 terms of the expansion of e to the x times the sine of x. And that concludes Calc 2.